I'm using the same recording software that they use on Twitch. So should I just broadcast to Twitch one day? You know, put it under the science and technology streams. You know.
And then people like Braden, when they miss class, they can be like, "Sorry, I missed class. Here's 1,000 bits."
Yeah, let's not do that. Yeah, let's not.
I feel bad.
With the automatic speech to text thing, like as we're lecturing. No. That's not happening. That's not happening. All right, everybody, let's get started. I'm actually going to pull something up real quick after everybody gets the code, because there was actually a little, somewhat interesting discussion about like the homework and what it meant, and I thought that was kind of cool. But first off, let's go through some logistics. So the last homework, I think, still being graded, but the solution is posted. How did homework 2.4 go? Go well? Good. Yeah, we were talking, because if you remember in class, I said something like, I don't know if it's going to pass slenderness, if it's going to fail slenderness, if it's going to pass strength, it's going to fail strength. And suffice it to say, one passed and one didn't, right? And so one of the questions I had right before class is, what does that mean? Like, what does that mean in the real world? And so I found a picture online just to guide the discussion, because I thought it was kind of interesting. I'm going to zoom in a little bit. Oh, goodness. Here we go. So I'm sure you all have probably seen buildings like this. This is something you might find like a warehouse, or maybe like a gymnasium or something like that. These are common portal frame structures. And so the tension members in a structure like this are these like small elements like this. So like this element right here would be a tension member, because it's sort of keeping the structure stable laterally, right? So what's happening is, imagine like wind or something is pushing the structure from left to right, and it's these tension rods right here, which we are going to do threaded rods here in a little bit, but these tension rods are what are keeping the structure stable. And so what would happen if you started getting like a really, really slender element is you would see that this thing would be sagging a little bit. That's kind of what that meant. That does not mean the structure is going to fall down and kill people, but it does mean that it's not performing its intended function. Also, if it's really, really slender, it can just be hard to handle during construction. It can be hard to put together. So again, like there is no definitive rule that says that you must adhere to L over R less than or equal to 300, but most folks are going to employ that just for common sense sake during the construction perspective, or during the construction portion. Okay. All right. So today what we're going to do is sort of a repeat of the lecture on Wednesday, but I've got another example. It's different. Okay. So what I mean by that is some of the decisions that we made on the in-class example on Wednesday are not going to be the decisions we make or the conclusions that we make about this one. There's going to be different ways, different methods that we need to use to analyze it. But I really want to kind of reinforce the notion of steel analysis. In other words, here's a member or here's a connection, assess it, determine its capacity. And then what I'll probably do today is highlight what that means in terms of design. Okay, so I'm going to go through this part real quick, because there's this slideshow is pretty much a copy and paste from lecture 7, except for the last slide, but because it's all the same. So let's just make sure that we're clear. In LRFD, we're dealing in factored loads and factored resistances. So this part, I think it's fair to say that I had been mentioning this for a while, that, here's what we're doing. And I think probably now you finally get what I'm talking about, that it's like, okay, we're going to look at the limit states and compute capacities according to them, and then we're going to look at our factored loads, and then we're going to see how they compare, okay? We have our load combinations, and I think it's fair to say that for the vast majority of problems that we do in this class, 1.2 dead plus 1.6 live is going to be the situation that matters. Now, I want to say that one of the things that we are not going to talk about in here, but it is something I kind of just want to highlight, is the idea of staged construction. So here's an example of staged construction. I'm going to give you a bridge example. So if you're working on a steel bridge and you're erecting that bridge, so just think about the process. So you've got your river that you're crossing or your overpass that you're crossing. So, the first thing is folks like Dr. Knott come in and get all the substructure, get all the piles in place, and get all the abutments and whatnot configured, what the bridge is sitting on, okay? Then you set the beams down, and then you form up the deck, set your rebar, all that, and then you place your concrete deck. Bring in the concrete truck, place the deck, screed it, and so on and so forth. Let the concrete deck cure. Then you start placing barriers and overlay, let the traffic run over, right? Okay, so let's think about that from a structural engineering standpoint. The steel beam by itself has to be strong enough to withstand its own self-weight. It has to be strong enough to withstand the cross frames, the bolts, the stay-in-place formwork, the rebar, and the weight of the wet concrete. Am I correct? Is that a fair statement? Okay. Now, but here's the thing. What happens to wet concrete after you place it and let it sit there for a little while? It cures, right? Now, how many of you have ever been on a DOH construction site for a steel bridge? How many of you have ever seen one? So, can somebody tell me what the top of the steel beam looks like? Like, is it just flat? You're shaking your head no. Why? You're shaking your head no. Why? It's not flat. Is there something on top of the steel beam? What's it look like? Let me ask this. Does it look like this? So you've got a steel beam. Yeah, so you've got these like little nail things that are sticking up on top of the beam. Y'all know what I'm talking about? Have you seen these? Okay. Why are those there?
Hold the concrete in place?
Exactly. So as you place the deck, the concrete interlocks with those studs, and it makes the beam what we call composite, okay? Now, what is composite behavior? Here's what composite behavior is. So I have here my steel manual, and if I take these pages and I bend them, it's really easy to bend them. And the reason why it's easy to bend them is I'm not bending one beam. I'm bending like 500 beams that are all really, really tiny, okay? Now imagine I had a whole lot of time on my hands, and I took each one of these pages and I glued them together, okay? And then I tried to bend them. It'd be a lot harder to do that, wouldn't it, right? Because it wouldn't be 500 little beams, it'd be one really big beam, right? They'd all be behaving together. And when I say composite behavior, that's what I mean, okay? So here's my point. During construction, the steel beams by themselves have to be able to withstand all of that dead load. Whereas once the concrete deck cures, it is the steel beams and the concrete deck together that withstand the live load. Does that make sense? So when I say there's different load combinations, it's like if we really wanted to get into some advanced design, which we may touch on a little bit near the end of the semester, but what I'm saying is when we get into advanced design, it's not as simple as just take a bunch of loads, plug them into these equations, and get the maximum. It's, okay, here is this situation. We have these loads, and it's just the steel beam by itself. And then we have another situation where here's these loads, and it's the steel and the concrete acting together. And that's what I mean when I say staged construction. And it is possible that if you think of things in terms of performance ratios, that the beam actually sees its worst conditions during construction, okay? That's actually the worst state of stress, the worst design condition is during construction. That once you get the concrete deck on there and that it cures, the bridge is fine. It's like a good example of where that might happen is, how many of you, did y'all ever get a chance to go see that I-64 bridge in Nitro? The big one, you know what I mean? The one that they recently poured. Did anybody ever hear them tell stories about when they were placing the deck and they heard all these like pops and it was, ooh, I mean, think about that steel beam by itself having to withstand about 10 inches of concrete that big. That ain't exactly feathers. That's a lot of force, you know what I mean? But once the concrete deck cures, the steel beam and the concrete itself are withstanding the weight of the traffic. I bet that the worst state of stress during the life of that bridge was during construction. That once you get the concrete deck on there, that bridge is fine. It's not going anywhere. And that's a common instance in steel bridge design, particularly in bridges with really complex geometry, that the construction state is the worst stress state. So you find that a lot in curved bridges and things like that. So I know I'm going off on a tangent, but I couldn't help it. Okay, So we have our limit states here. For tension members, we don't really see that because the tension member pretty much behaves the same throughout really any phase of construction. So we can sort of lump those together. So we have gross section yielding and net section fracture. Again, we're going to add a limit state to this list later. It's called block shear rupture. The equation for block shear is kind of messy, but the method is actually really easy. Once you start to see the pattern, it's pretty much the same stuff of what we've been doing so far. We have 0.75 FYAG and 0.75 FUANU. I think it's fair to say that what are the two most difficult parameters in this are net area and U. If you can get those, the rest is pretty easy. Again, this table, again, does not directly match what's in your manual because this is from an old edition of the spec, but I mean, it operates the same. You just take your greatest steel, look up the properties, and go with it. And whenever you have a range, you use the minimum. Here is our complete expression for net area, and we are going to use the complete expression today because we are going to have stagger in our example today. We have gross area minus the area loss due to the presence of bolts plus any necessary stagger factors. And to get the whole diameter, we take the bolt diameter and we add 1/8 of an inch because we're adding a 1/16 twice, one for erection tolerance and one for damaged material. Our shear lag factors, this is from the new manual, this is from the spec, the specification document. You just go through and assess which cases apply all of them, multiple cases may apply. But the big one you need to ask is whether or not you're either in case 1 or case 2. It's going to be either one or the other, okay, at least for bolted connections. So let's look at our example today. So this example is a little different in that we have an angle. There's two legs to the angle, and it's sort of, the stagger is crossing the legs. So like if I were to try and draw this isometrically, you know, what we've got is we've got like this, 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 and this, and then we have like this, this, and that. So we've got sort of a, oh, that's the wrong one. Try it like that. So we've got sort of like a stagger that's gonna like cross the leg. Okay, the stagger path is gonna go across the leg. So how do we handle that? Well, I'm going to show you how we handle that today. It's actually sort of, the answer is really like this. The answer is that we end up just sort of turning it into a plate and treating it like that. But how we handle the dimensions is something we have to take some care of. Bolts are 3/4 inches in diameter, and I'm saying the steel is A36. Actually, you can get angles in a higher grade now. You can get it in a higher grade than that. But we're just going to go with A36 for the purposes of teaching you how to use the table and whatnot. Okay, so let's get to it. Okay, so I'm going to take my keyboard off so I can, come on, there we go. All right, so what we're going to do is we're going to, in order to handle this staggered connection, what we're going to do is we're going to turn the angle into a plate. Okay, now the way that's going to work is we got to pay attention to our dimensions here. Okay, so we have here an L 5 by 5 by 1/2, okay? Okay, so what that means is that this dimension here is 5 inches, okay? And so what I'm getting at is it's 5 inches from the back of the angle to the tip of this plate. That is 5 inches from here to here. Likewise, this dimension right here is also 5 inches. Okay? Make sense? So I guess a question for the class is, if that's the case, what's this dimension? Okay, 10 inches, right? Wrong. It is not 10 inches. And some of you are thinking, now hold on, Dr. Mike. That doesn't make sense. Let me show you why. Okay, so let me show you why. Follow with me. Okay, so let's consider an L 5 by 5 by 1/2. Okay, because that's the angle that we're looking at. Okay, so here's the angle. Let me move this down a little bit. Okay. So, this dimension, I'll put it in here. This dimension is 5 inches. This dimension is 5 inches. Okay? What I'm going to do by turning this into a plate is I'm going to break out my secret weapon again, my samurai sword or lightsaber, and I am going to cut this right there. Okay? Now my question for you is, what is that dimension? 4.5. Okay? Okay? So what I'm going to do is this. I'm going to have sort of this plate right here that's been cut that's 4.5 inches. And then I'm going to have this other plate, which is right here, where you can see this is where it was cut. And this dimension is 5 inches. Then what I'm going to do is I'm going to take this little plate, and I'm going to stick it on top like that. Okay? So what I've now got is a plate that looks like this. And here's where that little nub is right there. This dimension is 4.5 inches, and this dimension is 5 inches. So my question, let's ask that question again. What is that dimension? It's not 10 inches, it's 9.5. Because if it's 10 inches, you've double counted that thickness. Does that make sense? Is everybody okay with that? So now, in terms of figuring out our remaining dimensions, here I'll clear that one up. That one looks messy. So in terms of figuring out our remaining dimensions, this is sort of our issue, right? Okay. So let's see if we can figure some stuff out up here. Okay, and then I'm going to redraw the plate down here just to sort of clarify everything. Let's see if we can figure some stuff out. So what is this dimension? 1.5. Okay. Let's see. Let's see about this dimension here. Let's see if we can figure some stuff out. What about this and this? So what I will do is, so see how instead of this being 10, and instead of this being 10, it's 9.5? We cut a 1/2 inch off, right? So how about this? From here to here, it's 2. So we'll say maybe this is 2. If we say this is 3, that's going to be wrong, right? Because we'll have overlapped, right? So maybe what we ought to do is say this is 2.5. See, I propose that from here to here, it's 1.5. From here to here is 2. From here to here is 3. So we could say this dimension is 5 inches, but we'd be making the same error if we said from here to here is 5 inches that if we said from here to here is 10 inches. We're overlapping, right? So I propose that this dimension is 4.5. Does that make sense? So if I redraw, I'm going to redraw this plate, okay? I'm going to redraw it down here. I propose this is what it's going to look like. All right? So here's what we got going on. So here's me yanking on the plate, and I've got a hole here, hole here, hole here, hole, 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 hole. And then what I'll do is I'm going to raise these just a little bit. Okay. And the other thing is I'll go ahead and put like a dashed line through here to sort of indicate where I turn that into a plate. Although the dashed line doesn't really matter anymore, okay? And what I'm going to say is that this dimension here, we'll call this dimension 1.5 inches. And we're going to call this one 4.5 inches, okay? So what I will do, now let's just make sure that we're clear. Are these going to be S values or are these going to be G values? G. So what we'll do is we'll call this G1, G2. And then this dimension right here, what was this again? What was that dimension? 1.5. So we'll call this S is 1.5 inches. Okay? Does that make sense? Do that a little bit. Okay. So again, just like what we're saying is that this dimension right here is 9.5 inches, we are saying that this dimension is 5 minus the thickness, because this right here is 10 minus the thickness. Does that make sense? Okay. So again, so this is essentially 10 minus a thickness. G1 is 5 minus a thickness. So, because both of them would account for that overlap twice. Okay. Now the other thing I'm going to do is just make sure that we're clear on something. Which is the lead line? Is the lead line these bolts over here? Is the lead line these bolts over here? The ones on the left or the ones on the right? The right. Okay. So that means our failure paths are going to go essentially along these bolts here. Now let's make sure that we're clear. Let's put some letters here. How many failure paths do we have? How many paths do we have? Somebody name off a potential failure path.
A, B, D, E.
A, B, D, E. And then,
A, B, C, D, E.
there we go. Are there any more? No, there aren't. I want you to be confident in that. Any other bolt or any other path would shear a bolt, right? Okay, with me so far? So now that we've got this, we can do some work. Now, we have an angle. We need to compute gross area and net area, but here's the thing. We could compute gross area by just taking 9.5 times the thickness, but that's going to be slightly off, okay? Because the real angle has some rounded edges. Like if you look at the real angle, it's got some rounded edges here and here and here. And so if we just do 9.5 times the thickness, we're going to be off on our dimensions. Instead, we're going to look up the properties of the angle, okay? So now, let's go to that. Let's go to an L 5 by 5 by 1/2. This is going to be in table 1-7. And I don't know what page it's on, so we're going to have to say it again.
46.
46. Okay. Okay. So we're definitely going to need the gross area. And what is the gross area? 4.79. All right. Now notice if you took 9.5 times the thickness, you get 4.75. So the gross area is a little bit larger in the manual than if you just treated it like a plate. And the reason is because you got those little rounded bits. Okay, and they are areas, so we're going to count for them. We do also need a thickness. Now, This problem said just determine the capacity. So we actually don't need a radius of gyration or anything like that, okay? I'm just gonna, I'll leave that part silent. Now notice if we did need a radius of gyration for slenderness, which one would we look up? Rx?
Doesn't matter, they're the same.
Hold on. Rx and Ry are the same.
Oh, RZ.
RZ is smaller because it's about that principal axis. So we would use RZ, but we're not using it since we don't need it for this problem. Okay. Now I'm going to go ahead and look up A36 steel. A36 steel is going to have an FY and an FU. That is going to be in table 2-4 on page 2- I think it's 54? 56. Again, it was 48 in the last one, so I just can't remember it. So let me move this over. So what's FY and FU?
36 and 58.
There we go. Remember, when you have a range, use the minimum. And then lastly, we know that for our bolts, we know that the bolt diameter, what was the bolt diameter in this problem? 3/4. So that's that. By the way, I am using this term effective hole diameter because when we get to bolted connections, we're going to use hole diameter. So we're actually going to have different diameters there. And so I'm using my notation very specifically. Okay. All right. So net area. We've got two potential net area paths. So let's handle both of them. Okay. So net area. Okay. So what I'll do is I'll say net area for A, B, D, E equals the following. So how do I compute the net area on path A, B, D, E? How do I do that? Let me make sure everybody can see what we're talking about. So we're looking at this path right here, A, B, D, E. So it's the gross area minus, tell me what to do.
Minus 2.
All right, any stagger? No. Okay, so gross area and diameter times the thickness. So and that's 1/2. So what do we get for that? 3.92 square inches. Do I have a second? Am I good? Because I know Mr. Humberson brought his Casio FX 115 ES Plus or similar scientific calculator.
I did. He's holding it.
Oh, okay. So you graciously let him
Yeah.
use it. Okay.
He's got to learn to read somehow.
I should have gone. I'm sorry, Mr. Gray.
Seconded.
Seconded. Thank you, Mr. Gray. All right. Now,
That's at 9.
AN, A, B, C, D, E. I heard about your shear lag factor debate as well, dude. Okay. Okay. Now, the gross or the net area equals the gross area minus, now how many bolt holes are we going to subtract? 3. Okay. Now, here's the thing. How many stagger factors do we add?
2.
So we add just 2 stagger factors, right?
2 separate, but they're different.
There you go. That's exactly right. They're different. They're different because they have different distances. So what I'm going to do is I'm going to say S squared T over 4G1 plus S squared T over 4G2. They are different stagger factors because they have different gauge distances, okay? So you can't lump them together. You have to treat them separately, okay? So what we'll do is we'll chug this out down here. Oh, whoop. So equals 4.79 minus 3 times 7/8 of an inch times 1/2 of an inch plus and there we go. I'm gonna scooch those together a little bit. Okay. I'll get everybody set and see what they get for this. Did I get all my parameters right? I think I did. There's the here. 3.73. Do we have a second? I want to wait on this because this one's a little long. Okay, we got a different answer. 3.56. Okay, we got a second on 3.73. And that's what I got. So what's our net area? Is it, which one? The smaller one. And what we'll say, that one governs. Because think, if you're yanking it, you're going to yank through the path that has the smallest net area. Okay. So, what's left? In order to start computing capacities, what are we missing? What's that? What are we missing to compute capacities? Shear lag factor. Shear lag factor. Okay. So, we're going to get our shear lag factor. Put it down here. (16.1-34). And I'm going to let you all drive the train. Tell me what to do.
2 and 8. Or no, wait. No, 1, 2.
Hold on. I'm hearing some answers, and I think we might have resolved this, but remember, whenever you're looking at your shear lag table, the first thing you want to ask is whether or not we're in case 1 or case 2. What is the difference between case 1 and case 2? Case 1 is that all of the elements are connected. Case 2 is that some of the elements are connected. My question for you is, what is the deal with this problem?
All of them are connected.
All connected. So what's my shear lag factor?
1.
1. So U is 1. Now, if we want to have an argument about whether or not we can apply case 8, let's have that argument. What does case 8 state? If U is calculated per case 2, large value per minute used, we're not even calculating it per case 2. It's case 1, right? This is, all of the cross-sectional elements are connected. U is 1, right? It would be a case 2 and case 8 problem if one of those legs weren't connected. That make sense?
If we use case 1, is that always just going to be the only case we use?
Yes. Yeah, because the difference between, really, like, if you're talking about a bolted connection, it starts with case 1 or case 2, right? It's either all or some, right? And if it's some, case 2 would apply, but there's also other cases where that's the case. Now, so yeah. Yes, the shear lag factor is 1 in this case. Now, I'm sure there's some engineer out there who will probably say, yeah, but, maybe we should apply case A because it is a single angle with 3 fasteners per line or what have you. We can have that debate, but again, all of the cross-sectional elements are connected. Okay.
Well, in case one would still govern anyway because it's larger.
Yep. All right. So, but here's the funny part. You're going to like this. And my apologies, but you're going to like this. I must introduce you to a truth of structural engineering, and you will see that after this. What is the formula for gross section yielding?
29 AGFY.
That's right. So 0.9. And then that was 4.79. So what do we get for this?
155.2.
This is 0.75 FU ANU. So what do we get here?
162.3.
Okay, let me. Say it again.
162.3.
Okay. Here's the sometimes frustrating fact about structural engineering. Look at these two numbers, which one governs?
Gross section.
Okay. So, is anybody here annoyed at that? Does anybody know why you should be annoyed at it, or why you might be annoyed at it? We did all this work to compute net area, all this discussion about a shear lag factor, and it ended up not mattering. It ended up not governing. And the truth is, we don't know until we just start doing the problem. I mean, it's just the truth. You know, we can't understand that unless you can just look at the connection and see which one governs. I'm not that good. I can't just look at it and know that gross section yielding is going to govern. We got to do the math. But that's basically what happened here. We did all this discussion about net area and all this discussion about shear lag and ended up not governing. And so our answer is that. That can happen. That's just the case. So, like, I have done bridge designs before where, I mean, some of the math for flexural limit states is way more involved with this. And I have done problems where, you know, you go through all this math for lateral torsional buckling and all this, and then you do a fatigue check and you find fatigue's what governs the design. Like, that's happened. And that's just the nature of the beast. That's just how it is. So, all right, anybody have any questions on this idea? Okay, I want to end today's lecture by introducing design because I think it's finally time we start talking about it. So let's talk about it a little bit. Let's talk about design. Okay, so those slides I skipped over is stuff that we've already talked about today. All right. So let's talk about design. In order to design a member, we need to let's put yourself in the headspace of what's going on here. So what we've been doing now is tension member assessment. In other words, I tell you, here's the member. It's an L5 by 5 by 1/2. Here's the grade of steel. Here's the connection. I just want you to tell me whether or not it's safe or not. And so as long as you understand the math, it's a pretty rote process. You just apply the equations, plug and chug, and there you go. Okay? But design's a little different. Design is, you have no idea what the member is. You have no clue, right? I'm just telling you to pick a member that can hold up this much load. Now it's different. Now there's a lot of unknowns, and we need to be able to assess those unknowns, and we need to be able to come up with some way of picking an efficient member. So that's what we're going to talk about. So we've talked about tension member analysis. Now I want to talk about tension member design. And so to be clear, what I mean about when I say design is given some loads and constraints, we want to select a member to resist those loads. That's design. Okay. Now I want to establish some ground rules about how design is going to work in this class. Okay. And what I mean by that is we will always strive to select the lightest member possible. So if I had to choose between a W10 by 49 and a W10 by 39, which member do I pick?
Yes.
Why do I pick the W10 by 39? I mean, it's lighter. Remember, what does the second number mean?
Weight per foot.
Weight per foot. So why would I care about picking the lightest member? It's cheaper, right? We buy steel by the pound, right? So if I pick the lighter member, that saves money, okay? And so we will always pick the lightest member. And in general, that's what you're doing in the real world. Now, I want to throw a slight twist on that. We want to choose the lightest member possible, but we also want to, what we're really interested in is the lightest project overall. And so what I mean by that is this: if you have a building like this is a really complicated building. There's hundreds and hundreds of beams and columns and members and whatnot, okay? Sometimes as the structural engineer, it might be easier, so you as the engineer want to make every element as light as possible. So imagine you design every single beam uniquely, and you get 200 different cross sections, and now you go to the contractor and you say, here's the most complicated Lego set imaginable, have fun, you know? Instead, you might make the process a little easier by, instead of having every single beam unique, figure out the worst case beam and use it everywhere, okay? Yeah, that might make the structure a little heavier, and you might have some beams that are more inefficient than others, but if every beam is a W18 by 76, it makes it a whole lot easier for the fabricator and a whole lot easier for the contractor, and suddenly the project as a whole is a little cheaper, right? So I want to throw that out there. And then there are also other issues, like maybe if you want the W18 by 76, there's a 12-week lead time, but if you go with the W24 by 76, you can have it in 2 weeks. You know what I mean? So there's also those issues as well. And so we're going to use lightest member possible, but I do want to throw a little bit of a dose of the real world that you got to be a little flexible with how things work in the real world. Okay. The other thing that I want to throw out to you when it comes to design is that we are always going to constrain the problems in this class such that everybody arrives at the same answer. And so if I give you a homework assignment and I say, select the lightest tension member to resist this load, I could get 25 different answers and they're all right. You know what I mean? They're all work. I'm not going to do that. Instead, what I'll probably do is say, select the lightest W12 member that can withstand this. And suddenly, there's only so many W12s, and I've constrained it so we all get the same answer, okay? And I'm doing that for the purposes of the class. Again, you probably aren't going to have those constraints in the real world, but some of those constraints aren't that unrealistic. For example, if I have to design a column, so there's a column right there in the wall. If I have to design a column to withstand those loads, the architect said the column's got to fit in that box. So you got to pick a column that can fit in that box. You can't pick one that's like 24 inches wide, okay? So right there's a constraint, from the architect. That's not unreasonable, okay? So the constraints that I'm putting on here are constraints that you would find, in the real world. I might say, pick a member of this grade of steel. That's actually pretty common too, because most shapes are going to be available in typical grades. So again, we're going to try and keep the constraints as real as possible. Okay, let's talk about design, okay, and how we're actually going to do it. So when I say design, I mean select a member. So how do I do that? Let's look at my limit states, okay? Let's just take gross section yielding, okay? So just as an example, let's take gross section yielding. So gross section yielding, if all we were doing, if that's the only limit state that we cared about, just conceptualize that, it's the only limit state we care about. So we know that our loads have to be less than or equal to this, 0.9 FYAG. And if I tell you to select a member of grade A992 steel, then you know what FY is, right? So think, If I tell you to select a member, and you know what the loads are, and you know what Fy is, what are you solving for? You're solving for the area, right? So rearrange the equation, solve for the area, and you get that the gross area needs to be at least this. So what do? Open up the manual, pick an element that at least has this much area, and by golly gosh gee, it'll work, right? If all I cared about was designing according to gross section yielding, we're done with design. That is the termination of the lecture, right? I'll give you a load, pick a member that has at least this area, you're done, right? But that's not our only limit state. We've got two other limit states right now that we need to discuss. So what about slenderness? Well, slenderness says that L over R has to be less than or equal to 300. Well, okay, let's rearrange that, and let's pick a member that has a least radius of gyration of at least L over 300. Bam, there's two limit states. So if I give you a tension member and I say design this tension member for these loads, by the way, the tension member is 25 feet long, I can solve for a required radius of gyration, solve for a required area, pick a member. Done, right? There's a limit state that I forgot though. Which one did I forget? Net section fracture. Okay, that one's a little trickier. Okay, that one's a little trickier. Okay, the reason why it's trickier is so let's just think about that limit state. The net area is a function of the bolt holes, right? Well, how do you calculate the area of a bolt hole? You need the thickness of the plate that it's going through, right? We have no idea what that is because we're in design. We haven't picked the element yet, right? So how do we develop some nice little plug and chug expression for net area when we don't know what the member looks like? We don't. I'll do you one better. What about shear lag? Well, what about that? Shear lag is definitely a function of the connection geometry. We need the X bar value. What if it's a W section connected by the flanges and we need to know what the BF and the D value is? Like, there's too much going on with the tension or the net section fracture limit state to be able to just derive an expression. So what I'm going to do is I'm going to say that this, so remember, this is net area times U, okay? So I'm just going to say this whole quantity, I'm going to assume that it equals 0.75 AG, okay? So this is a guess. To be blunt, this is a total shot in the dark guess. It is a very educated guess, mind you. So if you look at all the homework problems we've done until now and all the in-class example problems that we've done until now, take net area times U and then take 0.75 times the gross area. They're not going to be that far off. They're good enough for a guess. Okay? So we're going to make a design assumption. We're going to assume that net area times U is equal to 0.75 times the gross area. So if we make that assumption, what we've got is this. So we've got 0.75 FU times the net area times U. You know, we set that equal to that. We say, okay, net area times U, let's make that 0.75 times the gross area. So I've got a 0.75 twice. I've got one for the phi value for the resistance factor and one for this assumption. Lump everything over here and I get this. So I get a new expression for net area, or for gross area. But the gross area is the load divided by FU times 0.75 squared, okay? So what I'll do is I'll say, look, I've got, this is the one for gross section yielding, this is the one for net section fracture. Let's just keep this simple and let's just compute one for the whole kit and caboodle. And what we'll do is, if we're trying to figure out which one governs our design, we'll just take the minimum of these two denominators, because the minimum of these two denominators is going to yield a larger gross area, which is going to yield a more conservative design, because we have to pick a member that satisfies both limit states. Does that make sense mathematically? Okay, so what we will do for design is as follows, okay? We will compute a factored load, and what we'll do is we'll compute these two design parameters. I'm going to call them the design gross area and the design radius of gyration. And then what we'll do is we'll go to the manual and we will pick a member that has these properties. The smallest member, the lightest member that we can find that has both this gross area and this radius of gyration. But here's the thing, the kicker is that we're not done there. We don't just pick a member and then go home. We selected that member based on some shot in the dark guesses based on what the areas are, right? We can't just finish there. The most important thing we have to do past that, we have to analyze that number. We have to go through everything that we just did for the past couple lectures. We have to analyze that shape to ensure that it actually does satisfy the capacities that we've predicted. And then summarize the results and compute the efficiency. And that's what we're going to focus on next week. And I'm going to talk a little bit, I'm going to mention this whole efficiency thing again, and then we're going to start getting into some problems and whatnot. So I don't want to go too far down the rabbit hole, especially given the fact that we're running out of time. But this is going to be definitely a discussion for next week. So everybody, you all have a wonderful weekend, and I will see you all on Monday.